go ahead and get started. So we left off on Wednesday. We had just finished this example. Just to kind of bring it up and remind you where we were, it was an example of a so-called double nested for loop. This example really wasn't doing all that much math, right? It was just calculating I times j to effectively make like a multiplication table style implementation there, where you have I loop and then you separately have a j loop, and you're just iterating through them. This is going to be a very common code pattern in the programs that you will be writing, and eventually it'll feel like second nature. I think it's certainly okay to just become more comfortable and more familiar with the single for loop. Again, for loops make a lot of sense when you're counting. When I know I'm going to be doing some action n times. Here explicitly n is the variable, but whatever it is in your program, I'm going to be doing something n number of times. For loop should be the next thing that comes to mind. You can write the structure of the for loop first, and then add your debug statements inside it, and then worry about what you actually need to implement inside the for loop. Because it is going to be harder to debug, to test, right? When you have just a single if statement, you're just testing one thing. You provide a couple different inputs, you're done. When you have a for loop, now for any given input, there's a lot of things your code's doing. So as we saw, keeping track of where you are inside your for loop, which value of I am I at, which value of j am I at, it's a pretty important debugging mechanism to have in mind, so that you can kind of slow things down, or just kind of trace back to where you got to, where you are in your code. And so for this example, we're just doing that multiplication table, but a lot of your double nested for loops are going to basically look just like this. Not necessarily n cross n or n squared iterations, but something times something else number of iterations, because what will just tend to happen, and I'm going to hopefully get to an example today where it's a less artificial example of this, is your data is going to have multiple dimensions to it. And we're going to want to kind of iterate through our data. If it's an image is the best example I can think of, and it has a width and it has a height to it, and we're going to want to just go pixel by pixel through the image and do some modification of that image or some analysis of that image, then this kind of code structure is just going to be a natural fit for that. So you do have to get to that point where you feel pretty comfortable with for loops and with doubly nested for loops in this example. I and j are just kind of historical variable names for our loop iterators. You don't have to call yours that. That's just very common practice. And so as we kind of look at this example a little bit more here today, we'll talk about a couple different little tweaks you can have in your for loops before we go through an image processing example today. One of the little tweaks or little side cases is that sometimes it can be very useful to exit out of the loops without continuing on, without going to the next loop condition statement. This keyword we've already seen in the context of the switch statement, and it's actually doing the same thing. In the switch statement, if the integer is equal to 7, and we're inside that case 7 block in our switch statement, and then there's the keyword break, that transfers control to outside of the switch statement. We break out of the switch statement. We leave the switch statement. Inside our loops, break also does exactly that. Break says, if for whatever reason, if there's an if statement guarding it or not, get out of our loop. I'm done with this loop. I guess you could argue prematurely done with that loop. My plan was, for this example of a double nested for loop, my plan was that I have my outer loop that's of size n, and my inner loop that's of size m. Technically, it's of size m plus 1. And if a certain circumstance holds true, in this case, if I happens to be equal to j, get out of that j loop. Get out of that inner loop here. Control will then basically flow to not the outside of the most recent curly braces, because that's our if statement here, but outside of that iteration of our for loop. And that's what the break keyword does here. Now, there's usually a scenario in which if you write program that has the break keyword, you could also write it that gives you the same exact functionality without having the break keyword. Instead of breaking, in this example, we could have checked if I is equal to j, or if I is greater than equal to j, and then just don't do anything and then just run the loop otherwise. But this is one way, if explicitly you know, I don't want to process that loop anymore if this condition holds true. I'm just exiting out of that most recent for loop, that innermost loop that I am currently inside. This can make your programs a little bit harder to analyze, but it does allow for functionality that otherwise would require more lines of code. So just to encode the same example, if I equals j, break. That break keyword says get out of my j loop. For a multiplication table, that could still be useful. What will happen if we break when I is equal to j? Okay, I was our rows, j's were our columns. So we're going to kind of have a lower diagonalization of our multiplication table, which is still valid, right? That still has all the same information in our multiplication table. It's going to miss the last element in the multiplication table. And hopefully you can visualize and see what's happening here. We have our little column and row headers here. It's maybe counterintuitive, but this one is J, right? Because of the nature of printing, we're always kind of restricted for now to print from left to right and then from top down, row by row by row. So that's our J index. This, which I'm not going to be able to highlight very well, that's our I index, our row headers here. And if we get to the point where I is ever equal to J, then we're breaking out of that loop. I would argue that this example would look slightly better if we did the break after we do that first printf, so that we actually get 1 times 1 and 2 times 2 inside our multiplication table. There you go, it's the same concept, just breaks 1 line later here. So when I equals to j, we have printed out the value, but then we're done with that row. We don't actually do the entire row for the entire j loop. We could have written our for loop that it would also just only print up until I equals j. This is just another way of transferring that control flow outside of the for loop without having to add more maybe complicated if statements inside the loop. There's also the continue keyword, which in this case, the way I have this written, wouldn't actually make a difference. Continue keyword is somewhat similar. It doesn't exit out of the loop. It says, let's continue on immediately to the next iteration of the loop. So some condition is true. Break says that condition is true. I'm out of here. I'm leaving this loop. Continue is instead, I'm done with this iteration of the loop. If there was other code down here, the continue would skip over it and then just go to the next iteration of that same loop. In my experience, break is more commonly used than continue, but there's scenarios in which both may make sense, in which our loops aren't as cleanly structured as what this example previously illustrated, and we just want to either exit out of our loops early, or we just want to short circuit the current iteration of a loop and just move on to the next iteration of that same loop. There really isn't that much else to say about break and continue. You will find some circumstances in which break is useful. It can also be useful as a temporary debugging thing, that I know I have some particular problem that pops up when some scenario is true with regards to my input. I'm going to explicitly add a check for that scenario in my code. Just exit out of the loop entirely, and then add all my debugging statements to figure out what exactly is going on with my program. We also need to talk about scope. It's not exactly directly related to this topic of loops, but it makes sense to cover it right now because it's also something that can be useful with regards to loops. So we'll start with a question. Will this code compile, or will this be a compilation error? Yes or no? What do you guys think? I don't know why it's highlighted so light looking, but that's just the syntax highlighting. So what is the potential issue? Why would I even mention about compiling? Right, which seems like bad news. Normally in a program, I have int a, and the next line I define int a again. That should be a syntactical error. Hey, you've already defined a. You can't go ahead and redefine a. At least in C. Other programming languages are probably more likely to be okay with that. This one will actually compile. Example 4.8, scope fun, because this stuff is fun. It's going to create a variable, initialize a variable, my var, to 0, print it out. It's got an if statement that checks, is my var equal to 0? Of course, if so. And inside that if statement, define a variable called my variable, set it to 1, print that one out, and then after that if statement is over, it's going to have another printf of my variable again. So what do we think this will print out? Just a guess. So 0 followed by what? Followed by 1. Absolutely. And then followed by what? Is it 0, 1, 0 or 0, 1, 1? Yeah, 50-50 chance. It's a binary thing. Okay, fine. Why guess? We have the code. Just run it. Executes, prints out 0, 1, 0. Now, I am not suggesting that this code pattern is desirable, but it's perfectly valid C. Now, it depends. C as a standard has gone through evolutions over the decades. This is not that new of an evolution, but if you look at code that's more than 35 years old, it would not have been allowed. But since like 1989, you are able to do this, in which you have scoping rules assigned and associated with your variables. We'll come back to this example in a second. The definition of a scope of a variable is the block or the region of code in which the variable is, I think the right word is accessible, or where the variable is valid. In general, when we define a variable in C, its scope or its availability or where it's valid is between its declaration and the closing brace of the block in which the variable is declared. This has not come up yet because so far, for every variable we've created this semester, where have we created it? We've created it within int main. We've had just a single function in our programs, and we're still just going to have a single function for now. And we've put all of our variables basically at the very top of that function, at the very beginning of that function. So if we just go back to that very kind of formal sounding definition, the variable scope, the variable's availability and validity rules is between where it's declared and the closing brace, the closing curly bracket of the block in which the variable is declared. So what we've been doing by default, and maybe we can even just look at this prior example versus the current scope example for our variables, is we've declared them pretty early on after int main. So where are those variables? Where have they been valid for us? Between where they've been declared and the closing brace of the block in which they were declared, which for us is the entire program, basically, right? That's not to say we could still have scoping issues. I think you'd look at this and say, obviously this is wrong, but I can't do I equals 3 on this line, because that's before it's been defined. So, you define it and then you can start to use it. I think we have that intuition, but that's the more formal reasoning of where a variable is valid, where it can be used, and the other term we're using, where the scope of that variable is. So it's not really an issue that we have to declare our variables at the top. That is not a requirement. Like on different lines, or you could. There's nothing wrong with doing that. Well, let's talk about that. Now, why did I do that? Habit would be the honest answer. When we talk about scope, we'll see maybe I and J are going to be a slightly different case than the variable n for this particular program because of these scoping rules. So going back to scope fun, and I think we can all agree that this is very fun, We have this first my variable and its scope, where it is a valid variable in my program, is between where it's defined and the closing brace. So that's int main. But any block of code that has its set of a pairing of braces can define its own scope. So while it may not be that common to see that defined this way, it's perfectly allowable, it's perfectly valid, that this if statement is its own scope. So this variable is a different location in memory. It is a different variable. It just happens to have the same name. And the scope of this variable, my variable defined on line 8, is between where it's declared on line 8 and effectively the closing brace on line 10. So that's why this one prints out 0 and this one prints out 1. Now when we get to line 12 here, it's indirectly related to global variables with regards to the scope of those. We haven't been using global variables by and large this semester, other than when we did that example where we were printing out the location of variables and they were in different locations based on where we defined them. And that is also related to scope. One is a spec of the language, the other is an implementation of the compiler. So they're related, but they're not directly the exact same thing. Going back to the scope issue first, that's why in line 12 we're printing out 0 for my variable, because the my variable it's referring to is this one here. This one here does not exist. It's not valid outside of its scope, outside of those lines of code in which it's defined, that the curly braces in which it's defined here. That's not to say it's a good idea to have multiple variables named the same thing. It's just that it is allowed, and when we have our loops or we have our if statements, and I would argue for loops it's more common to do this, and certainly when we separately have our own functions, the variables we're defining for those loops or for those functions are wholly separate than variables that are defined in other functions or inside other loops here. They may have the same name because things like I, J, and N and these other variables are just going to be common names we're going to be using over and over again. But they're going to be different variables. They just happen to have the same name as some other variable with a different scope inside our program. We will have to keep track of this, and this will be another kind of common class of bugs. Certainly as we jump into other variables, or into functions as a separate topic, this kind of visualization can be somewhat helpful. We also could have a memory visualization of where things are being physically placed. But if you have a high-level structure of all your programs in which we have our main function, and I'm not even showing another function here, we have variables that are defined inside main, have scope for all of main. Then consequently, if we have any sort of loop, any variables we define inside that loop have scoping inside that entire loop. And while I would argue it's less common, even inside any of our if statements that have those braces inside our loops, if we define a variable inside those if statements, the scoping of those variables are only valid inside those if statements itself. But you can also think of it as being kind of a top-down view of scope, of sort of outside in terms of scope. It's inclusive. Where can I use the variables at various locations inside my program? So you asked about global variables, and this example does illustrate that use of a global variable. There's a lot of downside of global variables, but sometimes they do make our life a little bit easier. In this case, we can think of this as this variable is defined outside of any braces whatsoever. It's actually going to get placed in a separate region of memory for that reason. It is global in scope. That's why we refer to them as global variables. Other languages have a keyword called global, where you say, this variable is global. C doesn't have that. We define our variables to have global scope by just defining them outside of any particular function. Consequently, anywhere in my program, I can refer to global variable, and the compiler will know what that means and allow us to do work with that variable. Then we have our main function or any functions, and the variables we define inside that function have that scope only within that function. So within that function, at any place, we can use that variable called function variable or that variable called global variable. If we had a completely separate function, we could use the global variable, but that function variable would not be valid inside that other function. And to go back to this intentionally, silly example here, if we separately defined another variable called function variable, it would be different. The values wouldn't propagate. That's why we get 0, 1, 0 here. We updated this other variable. It just happens to have the same name. It has otherwise nothing to do with this variable defined here. So the scope kind of progresses from outside in. So that when we're inside that if statement, we have this variable that only has scope inside that if statement, but we also have access to all the other variables that have been defined in that broader scope. So for the most part, we don't have to deal with this if we don't want to. Define all your variables at the beginning of main. They'll all be valid for the entirety of main. When you now have a second function, then you have to be a little bit careful, because if things aren't defined inside that function, you won't be able to access them. If we truly have some global state that needs to propagate across all the functions in our program, we can use a global variable for that. But otherwise, we need to be aware that these scoping rules exist. The other place we tend to see that as kind of a shortcut for defining variables is with these for loops. C allows you to reuse variable names at different points in different scope and declare them at different points in a function. By and large, this is just my opinion, best practice is still to define your variables at the start of your function. Here are the variables my function is going to need. I'm going to define them at the top. The downside is, I may forget my variable names as I keep writing code, and I'm going to introduce typos, or I'm going to have to keep scrolling back up and see, what did I call this variable? Did I call it my temp or temp1, or what did I call it? I have to kind of remember it to avoid syntax errors. But that's another rule of thumb that we're going to try to follow this semester, that we can put our variables at the top of a function because we're going to try to keep our functions relatively short and try to be able to keep them all on one screen at a time. And if you're having to scroll and scroll and scroll through your functions, maybe that tic-tac-toe example required a little bit of that, you are going to have more bugs because you're going to kind of forget what things that I defined, did I initialize them, what are the values at any given point in time. If you can't remember, it is tempting to put the variable closer to the code in which you're using them. That can be okay, but maybe as a sign you're trying to do too much in a single function. Maybe you should be splitting up the functionality. But the other place we will use that scoping rule as something of a shortcut is if we have a lot of I and J loops in our program, and we see ourselves just kind of reusing I and J over and over and over again. This is a very common thing you will see in C code, for which we define the int I variable only local to that loop. It's a variable defined effectively just to iterate through our loop. It usually is only being used inside our loop. If we go back to our multiplication table example, n is used outside the loop, so defining n up here I think makes a lot of sense. But as we have this j loop here, we use j, we initialize it to 1, we check to iterate between 1 and n, and we don't use j again. We have a separate j loop, initialize it to 1, check to see if it's less than or equal to n, don't use it again. And then for our ij loop, we initialize both I and j. We don't really use them after the loop. They're not required to have scope of being only local to the loop, but that's a very common thing we will see, in which we're effectively then going to be redefining those variables local to the loop in which we are using them. Does that change better or worse than the previous example in which we defined I and j at the top? It's neither better nor worse. It's just a different way of keeping track of the variables we have in our program. In this way, and it should give us the same exact result, we're intentionally limiting the scope of our variables. That does limit, right? If I really wanted to know what the value of I and j are after those loops are done, we actually can't do that if we have such a scope. because that would be a compiler error. And hopefully the highlighter would tell us that that's the case, and it does. And you may look at this and say, okay, that's such a weird error. Use of undeclared identifier I. Well, that's nonsense. I've declared I and I've declared J multiple times in this program. Maybe a better compiler warning or error would be something like, you have an I and a J, but it's not in scope, so it's not valid on line 51 of your program. I mean, that's the linter warning. Let's see what the actual compiler error you get back out is. It's the same. Use of undeclared identifier I, use of undeclared identifier J. When you get that error and you know you have an I and J in your program, it's likely an issue with scope. I don't think this will be that big of an issue with regards to for loop. As we start to split our code across multiple functions, that has to be part of our problem-solving strategy. What variables do I need to have in any particular function? What variables do I have to actually kind of pass back and forth between functions as I call them? That has to be just part of the problem-solving strategy, where today we already do have to think about the variables that we need. In this case, n is the only real external variable here that we're entering in. As we start to split up our code across multiple functions, not just what variables do we need, but what function should the variables be resident in. There's a temptation just to declare everything global, and then you don't have to worry about what functions variables are defined in. That's not very good practice. It leads to all sorts of challenges in compiling more complicated programs. Questions about scope, variable names. Okay. So what I wanted to do with the remainder of our time here is to bring up one of the examples for this upcoming lab that you've already hopefully gotten started a little bit with. This is a good example of what more realistic C programming tends to look like in practice. In some sense, now that we know loops, or we're about to become more familiar and comfortable with loops, in some sense, you know all the basics already. Yeah, there's more things we're going to be learning. So the semester's not over. We're only a third of the way there, right? But you have enough to get going. Arrays as our next topic will help with some of the kind of programs we'll want to write. But this example doesn't use arrays. When we start, string processing as a separate topic is pretty important as well. So there's other things we do have to learn. But you definitely have enough to write quote-unquote real programs. I think you will find that a big part of programming in general, and with C is no different than other languages in this sense, is so much of the code we write isn't starting from a blank file and just starting to type. Beyond just the problem-solving process we like to follow, it's understanding what other code already exists, what libraries, what APIs, what other applications are already there. How can we make use of those to build more advanced programs without having to start from scratch? In some sense, there's this incredible bounty of 50 years of C code that have been written that you can link against, that you can make use of the code that's already been written, and you don't have to start from scratch. And that's a wonderful thing. That's part of the reason C is still such a popular systems language. On the other hand, this becomes kind of the primary challenge. Not writing code from scratch, but understanding how to use other people's code. And I don't have great tips for how to do that other than to just have examples in practice this semester in working with other people's code. So we've done a little tiny bit of that, but that was back in lab 1 when we were just kind of trying to get our feet wet and understand things. So now in this upcoming lab, there's a proper image processing example. It is still an example where it's just have fun with image processing, so there isn't super high stakes associated with it. But as part of it, you're using an image processing library called libgd. And libgd is actually quite powerful in terms of reading and writing to image files and allowing you to access individual pixels and do other things with regards to image analysis and image processing. When you're faced with a challenge of write code that's going to interface with this library, there's a couple different places you want to look. And I talked about this, but this was far earlier in the semester. Ideally, at least for me, I think your best place to look is if you can find a tutorial. someone who's already gone through the steps that you effectively will have to go through, and here's some sample code that does exactly, a hello world example in that library. I'll provide that for you, and I have provided that for you in this example here. The next place you generally would want to look would be in the documentation for that library. Documentation can be hard to read, and it's as much a part of programming as sitting there and typing things into your editor to make your for loops and while loops and things of that nature. It can be kind of unglamorous work too, right? That you're just sitting there, you're reading, you're trying to translate usually pretty formally written things into something that is back in English in your head that makes sense to you as you're trying to figure out how to apply this existing library to your code. And then finally, you can also look at the source file as well for a given library to figure out, okay, this is libgd. As part of libgd, what are all the functions that are defined for it? Let's look at the source code for them. If I really want to know how exactly this function works, and if it's an open source library, I can just look at the implementation. That can be pretty painful as well, because then you may have to be analyzing hundreds or thousands of lines of code to understand what you need to do next. So if you have a tutorial with demo code, that's the best place to start. Then you're going to be spending a decent amount of time looking at documentation. And then only if absolutely necessary do you then look at the source code for the library to figure out, okay, this function's not doing what I thought it should be doing. What the heck is going on? Let me look at the implementation to figure out what's happening here. So a big chunk of your programming life is going to be spent interfacing with other code. And your code is going to look very similar to what you've already been written. Declare variables, write some loops, do some if statements. That's it. I mean, that's all programming is at the end of the day. There isn't any more to it than that, right? In C, unlike some other programming languages, oftentimes the hardest first step is just to get that hello world working, example working for a given library. I keep calling it hello world, but I just mean like the most basic, I've gotten something to compile program that doesn't even do anything interesting yet. And it's for some historical reasons. It's also because C allows a lot of very low-level control over this process. But getting things to compile with a new library oftentimes can take a lot of effort. And it really depends. The approach that we use that works in Replit for this class may not work as you go to a completely different programming environment and want to use the same exact library. Replit uses a particular package manager called Nix. We've talked about it briefly. We don't have to become experts in Nix this semester because it's very specific to this environment. But as part of that, you can specify what packages you want to use with the programs that you're writing. So for this example, as well as the example in the lab, I have specified, amongst all the other kind of built-in packages, I want the GD package installed. I want this library for graphics development installed so I can use it in my program. There is definitely a chicken and egg problem here. I know I want to use this library. I know it's called libgd. They call it libgd, capital L, capital G, capital D. In the Nix packaging environment, it's just called .gd. How did I know that? I didn't. I had to Google it and read some web pages to figure out exactly what the package is named. If I switch from this environment to a Windows development environment, it's going to be called something different. To a separate Linux-based environment, it's going to be called something different. In your Mac, Apple operating system, it's going to be called something slightly different. That's not great, but that's just the state of modern software development these days. That part of it is a discoverability problem of, I know this library exists. Is it installed already? If not, how do I install it? What does it wind up being called when I do install it? And with C development, that's only half the challenge. So you have to install basically a development package associated with this library. That'll install the header files, the .h files. It'll install the pre-compiled binary blobs that include the implementation for all of these existing functions that you just then call in your code. That's half the step. And then the second half of the step is, at least in C development, we have to tell our compiler that when I'm compiling this program, actually use this library and include the code for that library with the code that I am personally writing and combine it all together into the final executable. That itself also sometimes requires looking up, how do I link in the libgd library? Nice thing about this particular library, this was the main page for their documentation, and the very first thing it tells you, because it does recognize that this is a fundamental challenge you have to overcome to get Hello World to work, is to use GD in your program, include the file gd.h, we'll see that in a second, and link with the GD library and the other required libraries. The syntax for most Unix flavors, which we are using, is this. -lgd, link in the GD library. -lpng, link in a PNG for those kind of images. LZ for compression, LJPEG for that images, LFreeType, I think for fonts, LM for math functions like sine and cosine and things of that nature. We have been putting those commands in a makefile. And I took the built-in provided makefile that Replit gives you, and I just took those commands and just added it to the flags that we pass our compiler to build it. So for this class, by and large, there's a brand new library we need to use. I'll get you started. Because that can take quite a bit of time to go from, I want to use this library, to now I have something that can actually compile and run. That's not even to look at the source code yet for that. It said, include the gd.h file, link with those link commands, and then you can start to actually use this library. And it's a decent starting page of the documentation. It even says, here is a short example program, which I basically just copy pasted into Replit, and it essentially worked here. Let's try to walk through this a little bit. There's a lot that I think we still have to take on faith at this point where we are in the semester, but we can gain more and more appreciation as we go here. We're going to be defining a couple of variables of a type that's not one of the built-in types, but it's the fundamental type that this particular library is using, and it's a data structure that refers to an image. One is just going to be called image or IM, and the other is going to be called image new. We're also going to be opening up some files in our system, and so we're going to want to keep track of the name of the files. So that's our first. This should look more familiar. Printf, scanf kind of loop, enter in a file name is what it's asking you. We're going to try to open up the file, check that it opens. In this case, if it's a JPEG file, we're going to use this library that's doing all the work for us to take the name of a JPEG file and load it up as this image object that has all the pixels and all the associated information corresponding to that image. And I think it's fair to ask, well, how was I supposed to know how to do that? You're right, I mean, I didn't tell you how to do that. Well, the tutorial has some comments, gives you some suggestions for how we can do these things. And even beyond that, then now it's okay. Now I look at the library, look at the functions that are provided to do various things associated with an image. You have to have some idea of what an image is. So if we have to go back to that, that's fine. But if you didn't have that, what is an image? What is a pixel? Well, then we'd have to kind of go back to the base principles from that. But once we have that understanding, well, what do we want to do with an image? I want to know how big the image is. Is there a function that tells me how big an image is? And there is. Is there a function that allows me to get a pixel? There is. That looks useful. Let me copy that into my program. I'm going to put it in comments because we don't have a place to use it yet. That looks like a useful function. Get a pixel color as stored in an image. There is also set pixel. That one also looks useful. There is no shortcut otherwise, though. Yeah, you look at the tutorial. It gives you some hints about what functions may be helpful. You have to have a plan in mind. There has to be some task you're trying to solve here. If the task is explore this library, then things like opening an image, saving a new image, changing pixels in an image are probably sufficient for the kind of things we want to look at. But there are, in fact, a lot of different things we can do in this library. We can detect all the images. We can set the image to grayscale. We can smooth over the image. There's some advanced stuff, and this is a pretty powerful library that we have here. But for now, at the very least, we have a function that our code reads in the name of a file. In this case, it'll be a full path to a file. We can create this kind of internal object that stores all the information associated with the file from that file name. For now, we can grab the width and the height of that image and print that information out. The other one I'm doing here, just to be able to do something with our image, is I'm going to copy that image, GD image clone. We'd have to look at the documentation for that. Take the image, copy it, and store it as a different file. So if the input image was steve.png, the new output will be steve_new.png. This code is all code I've provided for you. It's part of the lab assignment as well. It's basically the same exact starting point for that lab. Inside this replit that is provided, I just downloaded a few images for you. So I put it in a separate directory to not clutter things as much. So inside image, we can look at, let's do campanile.png. That's kind of a bigger one. Let's do campus.png. If I want to enter the name of a file to process, it's within the image subdirectory, local and relative to where I currently am. To enter in the image, I would also need to provide not just the name of campus.png, but that prefix of img for the name of the subdirectory. That's not a JPEG file, so let's see where it's failing. JPEG library reports under, okay. We would want to use the equivalent function that reads it in from a PNG. That seems like a flaw to me. I guess the code should probably check if it's a PNG versus a JPEG file and call the appropriate function. Okay. Opens up the image. Has a function that can check, given that image, what the width is, what the height is. We just add a printf to print out the image is of size 1200 by 800. Processing the image, but it doesn't actually do anything. That's blank there. And then store that copied image as campus new.png, but we haven't done anything other than copy it, so it should be an identical image back out. There'd be pixels. Pixels. So the individual RGB elements, I could probably open it up, and we'll see if this will actually work. Let's see. What would be I need like an editor though, let's see if I hit edit. I don't really use Windows editors for this kind of thing. Right, you have something that looks like this nice, this is a photo, right? A very nice professional photo of campus. It looks like it's very continuous, right? But when we zoom in, we recognize that what is this to our human eye, this very continuous thing. When I zoom in, let's see, this wouldn't shock me if I can't zoom in. This is a wonderful, let's see here, piece of software. Let's see if I can just do it in this one. I'm not editing it yet, but we can zoom in up here. Thank you. If you zoom in enough, and this is 1200 by 800, and on this projector, we may not actually be able to zoom in enough for you to really see it. Ultimately, let's see if I have a better, do I have Paint? Okay, I like Paint.net, it's fine. Ultimately, it's discrete pixels, right? We have a limited number of pixels that we're storing when we capture the image, and you can zoom in and actually see them. Okay, this would probably allow me to zoom in quite a bit more. There we go. Guess there's no point in zooming any more than that. that tree, which looked like, marvelous shade of green, is actually just made of this discrete samples. And each of those values it depends on how the image itself is stored, but I should be able to use like a color picker here, and it'll be based on, if you had it open, let's see, the color palette will be based on, depending on how the image is stored, but from our perspective, let's look at just a component of red, green, and blue. A certain intensity of red, a certain intensity of green, and a certain intensity of blue kind of added together. In this case, it's most likely out of 255. So that particular pixel is a little bit less than 50% red, a little bit less green than that, a little bit less blue than that. And that gives us that kind of brownish, kind of rustish.
Yeah, like 1200.
1,200 columns and 800 rows. So whatever 1,200 times 800 is total number of pixels. This is going to get us to some good places, but let's take the time on Monday to do it properly. So we're going to edit some images using the existing functions. And in the lab, you're really just being asked to kind of explore the same kind of technology to do something fun with it. But I think before we dive into arrays, I think it'd be good to use our knowledge of loops to do something like this with our images. Let's leave things here for today. Enjoy your weekend. See everyone on Monday.